Lesson 2.7, in lesson 2.7, we're going to continue talking about dilations on the coordinate plane. So in the last lesson, we talked about dilations and scale factor and the relationship there. And we're going to continue talking about both of those because you cannot have a dilation without a scale factor. Remember, dilation is the only transformation we're going to be dealing with that makes the shape or the figure get bigger or smaller. Okay, so to dilate a figure on the coordinate plane, you're going to multiply the x and y values in each ordered pair by the given scale factor. So that's why I said you can't have a dilation without a scale factor. So you're going to multiply the x and the y values in the ordered pair. Now it says describe what will happen if the scale factor is, this means greater than 1, right? Well, the image should be bigger than the preimage. Remember, the preimage is our original one, where we start. So if this is greater than, if it's greater than 1, then the image, the new figure, should be bigger than the preimage. Describe what happened if the scale factor is less than. Well, if it's less than 1, sorry, it's hard to see there, there's a 1 there, less than 1, the image should be smaller. The image should be smaller than the preimage. Okay, so it's really important that you pay attention to this part because that's what we should expect. Okay, if we have a number less than 1 and our image gets bigger, we know something's wrong. Okay, so now we have two things here. This is if we are given the scale factor. So sometimes they're going to say, here's a scale factor, dilate this figure. Sometimes they're going to say, hey, look it, here is the figure and it's the preimage and image. What's a scale factor? So when a dilation has occurred on the coordinate plane, you can find the scale factor by choosing corresponding sides or vertices and setting up a ratio. The ratio is the new image over the original or the image over the preimage. Remember, this is where we start to where we finish. So you always want to put the old one, I guess we'll say, on the bottom, the new one on the top. All right, so now those are the two things we're working on. Let's try some examples. Dilate the rectangle shown by a scale factor of 1/3. Okay, so we're going to dilate it and then we're going to record the coordinates. We have the scale factor. So remember, we're going to multiply the x and y values of each ordered pair by the given scale factor. I'm going to point out something, and I'm going to keep talking about it, but when you think of these points right here, don't think of them like you don't always put it perfectly on the inside. Here's what I mean, okay? And actually, it's not going to be a good example in this one. But we think of this distance from like 0, the origin, to R here, right? And if I'm dilating it by a scale factor of 3, remember this is less than 1, so it should get smaller, right? Well, not just smaller, but we want to think of it as being pulled closer to the point of dilation, okay? So if we were to break this up, right, into thirds, we're going to pull it 1/3 away. Okay, so it's not just the distance from 0. And this is not going to be a good example here, but I don't want you to always just try to make, if it's getting smaller or bigger, always put the other figure exactly in the middle because it's not always going to work like that in the coordinate plane. Okay, so don't just try to eyeball it, I guess is what I'm saying. And I'll keep talking about that so it'll make more sense. Okay, so remember what we're doing is we're multiplying, right? So the point A here, this is the point -6, 3. Now we're going to multiply the x and y value by 1/3. So I am going to go -6 times a third, which is negative 6 over 3, which is negative 2. Okay, so a prime is going to be at negative 2, and then I'm going to go 3 times a third, which is 3 over 3, which is just 1. So a prime is going to be at negative 2, 1. So if, again, you kind of look, if there's this line here, the distance from the origin to A, we decrease that to a third. It's a third of the distance, okay? That's what dilations do. But the quick and easy way is to do the points. So we'll do point B right here, right? B is the point, 6, 3. And so we're going to go 6 times the third and 3 times a third. Sorry, I'm trying to squeeze it in here. Okay, so A prime, nope, B prime is going to be at, well, 6 times 1 is 6, divided by 3 is 2. 3 times 1 is 3, over 3 is 1. It's going to be at the point 2, 1. So C right here is 6, negative 3. Okay, so doing the same math, 6 over 1 times 1/3. Well, we're going to know that answer already. Sorry, I'm squeezing this in. And then negative 3 over 1 times 1/3. C prime is going to be at 2. And then negative 3 times 1 is a negative 3 over 3, so negative 1. And finally, we have D at negative 6, negative 3. Not D prime. And again, we're going to multiply both of those by, sorry, those are both negative, 1/3, because that's our scale factor. So D prime is going to be at negative 6. 1/3 of negative 6 is a negative 2. Negative times positive is negative. Negative 3 times a third, just like we did here, is a negative 1. Now, remember, when we draw this, we anticipate that this shape right here is going to be the same shape. The figure is going to be the same shape, right? What's changing is how big it is. Now, because we multiplied by a number less than 1, we anticipated that it was going to get smaller, and it did. How can we represent the dilation algebraically? Well, make sure we pay attention to this one right here, right? What did we do? We multiplied both the x and y by a third. So our coordinate notation would say we're going to go 1/3 times whatever our x is and 1/3 times whatever our y is. That's it. Don't overthink it, because that's what we did. Now it says compare the ratios of corresponding sides. What do you notice? Well, the ratios of corresponding sides. Well, basically, I'm going to use kind of this idea here. I'm going to put my image over pre-image. The distance from A prime to B prime over the distance from A to B. Don't overthink this. The distance from A, oh, I didn't even mark those things. Oops, sorry. This is B prime, C prime. Always do this, D prime. Okay, so the distance from A prime to B prime is 1, 2, 3, 4. The distance from A to B is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, guess what 4/12 reduces down to? 1/3. Okay, well, what if we did B prime to C prime over B to C? Well, the distance from B prime to C prime is 1, 2 units. I'm just counting. From B to C is 1, 2, 3, 4, 5, 6. Well, what does 2, 6 reduce to? 1/3. Kind of get an idea here. If I go C prime to D prime over C to D, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Very sloppy. But 4/12 again is going to equal 1/3. And guess what? When we go from D prime to A prime here, or A prime to D prime, however you want to write it, guess what? That's going to be 2 over 6. And that's 1/3. So notice those ratios of corresponding sides equal our scale factor. Now, did the dilation change or preserve the orientation of the figure? Did this figure turn or face any other direction? No. How about the orientation of the vertices? Well, going clockwise, A, B, C, D. A prime, B prime, C prime, D prime. So did it change or preserve? Well, the dilation preserved. The orientation of the figure and the vertices, both. Okay, it's still pointing and facing in the same direction. All right, so that is the beginning to our talk of dilations on the coordinate plane. The big thing to remember is this. When we're given a scale factor, we have to multiply the x and y values by that scale factor to find our new points.